So today we're going to be focusing on polynomials in factored form. So day one was when your polynomials were in standard form. That's what we were looking at. Your equations were in standard form. We analyzed them that way. Now we're going to be analyzing them to find the exact same information as last time, but now they're going to be in factored form. So when polynomials are in factored form, they're going to look like this. So you're going to have a bunch of factors all strung together. So we've seen things that look like this before, right? When we factor, we've taken quadratics, which was all of unit 2, and we factored them, and that's how we get it to be in factored form. We're going to do the same thing with polynomials. There may be more than 2 factors, though. There could be 2 factors, 3 factors, 4 factors. We have a bunch of them. So this plus or minus just means that inside of the factors, you could be adding a number or subtracting. Okay? And factors could also have exponents. You could have exponents like this. You could have a 2. You could have a 3. Stuff like that. So your factored form of your polynomial is going to look a little bit more complicated than the standard form. So we're going to find the exact same kind of information. So each of these factors, we're going to call them linear factors because inside of the parentheses is just x with no power. So you guys notice that when we factored, it's always x plus something, x minus something, but the x itself didn't have any powers. We call that a linear factor because it's like a linear expression. And so if you guys remember, if I were to give you something like this from unit 2, and I ask you to solve that, what would your solution be? This would be set equal to 0, and then I ask you to solve. You would get x equals -2n, because you set them equal to 0 and solve, right? That exact same idea carries through into this context. So whenever you guys have linear factors, you can have a bunch of them. To find the solution, you just set that equal to 0, and then you would get the solution to be the opposite sign of the number that was inside. You guys remember that pattern? The solution is the opposite sign of what was in the parentheses. Okay. So just reminding you guys of that pattern, because we're going to be using that and applying it to the context as well. Alright, so we're going to find the same stuff that we did last class, the degrees, mean coefficient, turning point, and behavior, all that same kind of stuff. But it's a little bit different how we find that when it's in factored form. So think back to day 1, when it was in, let's figure out here, example, x cubed plus 3x squared minus 1, something like that. This is in standard form, right? So I said, what was the degree? What would you guys tell me? It's 3, you can see it right there. It's the highest degree, right? So if I asked you for the leading coefficient, what would you say? 1. It's right there, you can see it, right? But when it's in factored form, it's not multiplied out to look like this. So you guys can't just look at the front and say, oh, it's a 1. You can't just look at the highest exponent and say it's 2. You can't do that at this point, okay? Instead, what we're going to do is we're going to multiply this out. If we multiplied everything out, that would take us a really long time. You guys would have to boil this, and you'd have to distribute the x, and then whenever that is, you have to multiply it through this one. It would take forever. It's really complicated. It's just, ugh. So we're not going to multiply everything. We're only going to multiply the x. That's going to give us the leading term. This little step right here, we're going to find the leading term by multiplying all the x's, including their coefficients and powers if they have any. We're going to multiply them together. That's how we're going to find the leading term. So you guys can take your pencil or a pen or a highlighter or something, and I'm going to underline all of the x's that I see, including their coefficients if they have one. Okay. And then also, I'm going to, if your factor has a power, I'm also going to draw a little arrow like this. The arrow should be going to the x. Now, before we move on, I want to be very clear. I am not distributing the square. I had to move the signs because of the decorations, but you still cannot distribute a square if there's an addition or subtraction inside. I'm not distributing the square. I'm just noting that if I were to FOIL, if I were to do x plus 2 times x plus 2, with an x times x and that being x squared. So you still have an x squared involved. I'm just not distributing the square. I'm just reminding myself there is x squared. Alright, so now I'm going to write them out. So my first x is an x by itself. This x would actually be x squared if I were to multiply everything out. Again, we're just working with the x term here. And then this x term would be negative 3x. So you're going to write the x term from each factor, and then when I multiply those together, that's going to give me only my leading term. It's not going to give me the entire standard form of the polynomial, only the first term. So what happens when I multiply all those together? Negative 3x to the 4th, x to the 4th. So if I do 1 times 2 times 1, you add all the exponents together, gives you 40. Okay? So if I were to multiply everything and get the standard form, this would be the first term. There are more, I just don't care about them. Right? Because we had that example before, the only thing we looked at was the leading terms. I don't care about it. Alright, so once you do this, now you guys can do the exact same thing that we did last class. What's the degree? 4. What's the leading coefficient? -3. What would the maximum number of turning points be? Nope. It's 1 less than the degree. The number of turning points is 1 less than the degree. Okay? So again, we're just using the same thinking we did before. Still for end behavior as well. The degree is even. So that means both of the end behaviors have to be the same, either up, up, or down, down. And because it's negative, what would it be? So the way that you analyze the information is still the same as what we did last class. You just have to go one extra step to actually find what the leading term is, because the factored form doesn't tell you straight away. So you multiply all the x pieces together, get your leading term, and then you do what we did last time. Right? Also, I want you guys to be able to find the x-intercepts. We cannot find the x-intercepts from standard form. And find standard form. So that's the benefit of having factored form. You can find the x-intercept from factored form. And the way you do that is you solve. You take each one of your factors, you solve them, you're going to get an x value, and then you just write it as an x-intercept. So for example, my first factor is just x. What would the solution be from that factor? It would just be 0. If you set the factor x equal to 0, you get x equals 0. So as an x-intercept, you write that as 0, 0. Okay? What about this factor, x plus 2? What would the solution be from that? Okay, -2, how would I write that as an x-intercept? -2, 0. And then this factor, you have to set that equal to 0. This is what I'm doing, by the way. If you want to write words, this is what I'm doing. Just setting each of them equal to 0. So if I take my next factor, if I take my next factor, and I set that equal to 0, what would I get? Oh, yeah, -4. Okay, so again, whenever you're looking for x-intercepts, that's the same thing as finding solutions. So you set your factors equal to 0, find the x's, write it as an x-intercept, and you're good to go. That's the key thing you need to do with factored forms. We're going to use that to help us graph. Okay? Right, the next thing we're going to talk about is something called multiplicity. So we need to understand the idea of multiplicity in order to graph these things without a calculator. Multiplicity is a fancy word for exponent. So the multiplicity is basically telling you what the exponent is for a particular factor. So for example, if you're looking at a factored form, so I can go back up here, the factored form expression here, whatever the exponent is for each factor, that's called multiplicity. So this x, which has an invisible exponent of 1, you don't see an exponent of 1, this would have a multiplicity of 1. This one has a multiplicity of 2. This one has a multiplicity of 1. So whatever the exponent is on the outside of your factor, that's called the multiplicity. Now, the way that we use multiplicity is that when we're graphing, depending on the multiplicity of your factor, when you're graphing, your line could go, or your curve could go through the x-intercept, just go right through it, across the x-axis, or it could go up to the x-intercept and bounce off, which means it doesn't actually go through the x-axis. So if your multiplicity is odd, so if your factor has an odd x on it, you're going to cross the x-axis. And I'll show you what I mean when we actually get into this example. But if your factor has an odd multiplicity with the x-intercept that it generates, you're going to go right through that on the graph. But if it's even, you're going to bounce. And again, I'll show you what this looks like in a second. Now, think back to Unit 3 in our system. You guys remember when we factored, we got down to something that looked like this? We factored, the factor was exactly the same. You got two x's that were exactly the same, but I told you to write it once. Coming back to that idea, you guys have the same factors, you end up with the same x value. That's called a double root. How else could I write x plus 2 times x plus 2? X plus 2 squared, right? So this idea of the double root that connects with the bounce, the reason why it bounces is because because that x value is being counted twice. So the bounce kind of represents that. When it's a double root has an exponent of 2, it's representing that that x value shows up twice as a solution. That's why it bounces. That's what it's representing in the graph. So that's kind of a little background of why it would do that. Alright, completely ignore this. We're not using calculators at all. So what's up next for this lesson? This is the most intensive part of this unit. Okay? So we are going to create sketches of these graphs without using a calculator. And there are 3 things that you need to know in order to do that. I'm going to okay, I'm going to write this here. So 1, you guys need to know your end behavior. 1, you need to know your end behavior in order to graph this function. Number 2, you need to know your x-intercept. Number 3, you need to know whether your x-intercepts are crossing or bounded. With just those 3 details, you guys will be able to generate a good sketch, not a perfect or exact drawing, but a sketch of what the graph is. Okay? Alright, so I'm going to do these 3 with you, and then you guys are going to attempt to do the bottom 3 after. Okay? So for this first one, we need to find the end behavior first, and the only way we can find the end behavior is like what we did in the first box. We need to find the leading term. So, how do I find the leading term? If it was in standard form, you could just look for the highest exponent and away you go. But I can't do that here because it's not standard form. You're going to multiply all the x's together, just like we did in the first box. So I'm going to underline this x. I'm actually going to extend the line a little bit to include that negative, because that negative would technically be multiplied through. So this would be negative x, and then I have this x with the squared as well. So I'm going to be multiplying negative x times x squared when I multiply them together. So what's the total? What would that be? Negative x. So that's my leading term. If I were to look at this in standard form, my first term in the standard form would be negative x2. So based off of that, what would the end behavior be? What would the end behavior be? It's odd, which means that they're opposites, okay? And then it's negative, which means it has to end on a negative. So, that's it. Okay, so my end behavior is up, down. Now hold on to that thought. We're not going to use it quite yet, but hold on to that. The next thing we need to know are the x-intercepts. Those come really easily from the factors. Okay? So if one of my factors is x minus 1, what is one x-intercept? 0. Awesome. If another one of my factors is x plus 2. Negative 2, 0. Once you find your x-intercepts, go ahead and graph them. So I have 1 at 1, 0, and I have 1 at negative 0. The third thing you need to pay attention to is the crossing versus bouncing. That has to do with your x-intercepts, okay? So remember, if your multiplicity, so the factor, the exponent of your factor is odd, you're just going to go right through the x-intercept in the graph. But if it's even, we have 2. So basically, you're not going to use any powers higher than 3. So if your factor's exponent is 1 or 3, you're going to cross. If it's 2, you're going to bounce. Okay. So, for 1, 0, that comes from this factor. Am I going to cross or bounce through that one? Or 2 cross through this one. My negative 2 came from this factor, which has a multiplicity of 2. Am I going to cross or bounce? This one's going to bounce. I have a system that I like to use. You can either do this or not. For the points that bounce, I like to draw a little circle around them and call that a force field. So I know when I'm drawing, when I come to the force field, I have to bounce off of it. You can't pass through a force field, okay? So because I know that negative 2, 0 is bouncing, I like to draw a circle around it to remind myself that I cannot pass through that point. I just bounce off it. Okay? Now we're going to come back to the end behavior. Because the end behavior is up, down, on the left, my arrow will be pointing up, and on the right, my arrow will be pointing down. Once you have that set, now we're just going to connect the dots. If you guys ever do those connect the dots, you're going to start first, start at this arrow. You need to go to the first x-intercept on the left. You read and draw from left to right. I'm going to go down and touch this x-intercept. Am I going to capture it? Bounce off. Bounce off of it. Then you need to now go to the next x-intercept. Don't be jagged. Make it all these first. So now I'm going to go to the next x-intercept. Do I cross or pass? Or sorry, do I cross or pass? Cross, and then I get my bounce. So this is what your graph will look like. You bounce, cross, and then end the other row. This graph is all about that. I know there are a lot of steps, a lot of things to take care of, but this is how you would generate these graphs together. Any quick questions before we try it again? Okay. Went over. Again, the very first thing you want to do is figure out what the end behavior would be, so we have that kind of set before we start. So that requires knowing we use leading terms. How do I find these leading terms? Multiply all the x's together. In this case, only have one x. So what do you have to remember about it? That power on the outside does stick itself on the x. I'm not distributing, just noticing that when I would multiply it, my first term would be an x to the third, x to the third power. X cubed. My leading term is x cubed. So what would my end behavior be? It would be down, up. When your degree is odd, they're opposites. And when it's positive, that means that you have to end on positive. Positive. End on positive. So you go down, up. Alright, next, we're going to find our x-intercepts and whether they cross or bounce. So what would my one x-intercept be? I only have one factor. 1, 0. And then would I be crossing or bouncing? Why? This power is odd. So if your exponent for the factor is either 1 or 3 odd, they're going to be crossing. So 2, bouncing. Okay. Alright, so I'm going to graph my x-intercepts right here. And I'm going to graph my end behavior down, up. Now, because there's only one x-intercept and I see an arrow here and an arrow here, you guys would be really tempted to just draw a line. Right? But this is not a line, so the line would just be y equals x minus 1. There should be no powers if there's a line. So even though there's only one x-intercept, you guys still need to make it a little curvy. So it's going to look like that. Never draw a straight line for a polynomial like this. It will have a slight curve. Where that curve actually occurs, we're not 100% sure, but again, this is just a sketch. So, it doesn't matter much. Okay, questions about that one? This is a special case, this one here, because usually our cubic functions with powers of 3 have 2 turning points. This one only has 1 turning point, so again, that's one of our special cases where it has fewer turning points than that number we would get for the maximum. Alright, we're going to try one more, and then you guys are going to try it independently, so make sure you're asking questions if you're not sure about something. Alright, for our next one, first thing you want to do is find that leading term. How do I do that in this scenario? Multiply all the x's, so feel free to go ahead and underline them. Connect any powers if there are any, connect any coefficients if there are any. So I'm going to multiply x times x squared times, okay, so all of that would be my leading term. If I were to write this out in standard form, which is so much work, which is not going to, but the first term would be x to the 4. So based off of that, what would my end behavior be? Up, up. Because when your degree is even, they're both going to be the same. And because it's positive, up, up. Alright, what are my x-intercepts? 2, 0, negative 1, 0, and negative 2, 0. Very good. Now I need to figure out if I'm going to be crossing or bouncing at those x-intercepts. So at x, or sorry, at 2, 0, would that be crossing or bouncing? No. What's the exponent for the factor? So 1, so just crossing. It doesn't have to do anything with what the number of x is. It's talking about the exponent for the factor. I'll mix that up. It will be the exponent, not the number itself. Do not make that mistake. Alright, what about this one, the negative 1? What's the exponent of that factor? That's 2. So am I going to be crossing or bouncing? Bouncing. That's what you want to look for. It's really only going to bounce if the factor is being squared. Factor is squared, you're bouncing. Everything else, you're crossing. Okay. What about the x plus 3 factor? That's a multiplicity of 1, so then I'm going to be crossing. Alright, so then I grab my point. I have -1 bouncing, so I'm going to draw a force field. And then I have 2, 0, and -3. Grab all your points. Draw a force field around the one you're bouncing. And then I'm going to draw my end behaviors. By the way, when you guys are drawing these arrows, make them slightly offset from the closest exit. So go to the 2 ends and then slightly offset from the nearest exit. Alright, here we go. Ready to connect the dots? I'm going to start the arrow. I'm going to go straight to my first dot. Now am I going to pass through this or not? Okay, so pass through. Then I need to turn around and go to the next point. Pass through or bounce? Bounce. Okay, turn and go towards the next one. Am I going to pass through or bounce? Yeah, we're finishing it up. Pass through, and then I finish at the right side arrow. Okay, let's see how I did that. Now, if you were to check this, you can feel free to do this on homework. You're not going to have access to a calculator during test or test. But if you want to, on your calculator, your picture that you drew here is not exactly the same as what your calculator would give you. These little hills and dips could be deeper or shallower. We can't really tell. All I care about is that you guys have the end behavior correct, the x-intercepts correct, and that you're crossing and bouncing at the correct point. I don't care how deep. You can draw it like this. You can have them way deeper than I did, or way shallower. But it needs to have a clear kind of curvy shape with the hills and dips, but I really don't care how high or low they are. Okay? Any questions before I let you guys try on your own? Alright, go ahead and give it a shot. Just again to clarify for anybody who is confused, to determine if a point is crossing or bouncing, you look at the factors. Anything that's being squared is bouncing. Anything that's not squared is bouncing. That's really boils it down to the most basic way that I can explain it. If the factor is squared, that point is bouncing. If it's not squared, it's crossing. Okay. So this one should look like that. No, you just make your ear like slightly. That's what they should look like. Yep. This one right here on the third one, that gives you 0. When you set x equal to 0, you get 0. Okay? So we're going to stop there. We'll do the second side tomorrow. Make sure you guys are asking questions if you have trouble with this. This is what the majority of the test is going to be. So again, the absolute maximum is going to be the highest point on your entire graph. The absolute minimum is the lowest point on your entire graph. And then any higher or low point is considered relative. So if I were to ask for all of the relative maxima, you guys can do both of those 2 points. The relative maxima and the absolute maxima, those together is the entire set of relative maxima. But if I was just asking for one description for each of them, this would be the absolute and this would be the relative. Okay? So you guys see the difference between relative and absolute. Yes? Okay. So that was just a little aside to differentiate those two. Now we're going to do our problems from last class, but first. So I have provided a picture for you. We still need the same information as last time. behavior, we need to know the x-intercept, and we need to know whether they're crossing or bouncing, and we're going to get all this information from the picture instead of the function. So looking at the picture, what would the end behavior be? It's up, down. No, it's correct. So it's up on the left, down on the right, so your end behavior is up, down. Okay. Now we're going to write the x-intercepts, we're going to write them as roots. So that's the line right here, we're going to write them as roots, which means they have to be in the form x equals. So if I have this x-intercept right here, what would that be as a root? X equals over to -3. What about this x-intercept? 2, 0, and then right here. My x-intercepts are -3, 0, 0, 0, and 4, 0, but if I ask them in the form of a root, you would write it as x equals instead of as a point. Alright, so if I know that the solutions for the roots are -3, 0, and 4, I want you guys to now turn those into factors. If I know that I have a solution x equals -3, what would the factor look like that gets that solution? X 1, 3. Right? Remember that the solution and the factor, they're opposite signs. What about for 0? What would the factor look like that would give me x equals 0? Just x. And what about x equals 4? We have these factors, we have 3 factors for each of the 3 solutions. And now the next thing we're going to consider is the crossing and bouncing. So look at each x-intercept. What am I doing at this one? Okay, so all of them are crossing through, so am I going to have any squares? No, because you only square a factor if you're bouncing. There are no bounces here. So we can go right into the polynomial. We can have f(x) or y, depending on where we go. Right there. So f(x) our polynomial. We're going to have factors x. Actually, I'm going to put x in front. Because usually we write the ones without parentheses like a GCS at the front. You can put them in whatever order you want, but it's usually better to have the GCF one than the parentheses in front. And then the last thing you need to pay attention to, the first thing that we talked about was end behavior. Now we're going to come back to that. Thinking about end behavior turns bookends the thought process. So if my end behavior is up, down, what would happen to the leading coefficient that would give me an end behavior of up, down? It should be negative, right? So if you think back to what we were doing on the first day and the other side of the page, whenever we had a negative leading coefficient and an odd degree, it would always have that up-down end behavior. So you guys will have to include a little negative here, because it has that up-down end behavior. If it's a positive end behavior, if it was down-up and it's not positive, then it's not going to change anything. But if the end behavior indicates that you should have a negative leading coefficient, you have to make sure you put a negative there. Very important last detail to make sure you put that. And that would be your function. Okay. And then just as a reminder, we talked about this in Unit 0. Do you guys remember what this is? F of -2. What does that mean? What do you look when I say f of -2? What am I asking for? What do you want me for? A y value. Remember f of x is the same thing as y. So if I give you that notation f of something, so I'm asking for the value of y where x is -2. So all you need to do is go onto your graph and go to -2 on the x-axis and then figure out what the y value is on the graph. So I go to -2 and then I drop down to my graph is what about y value is that? Just a reminder, we saw that in Unit 0. If I give you that function notation, you go to the x value on the x-axis and then you go up either up or down depending on the graph to find what the y value is. Alright, questions about that? Alright, let's go to the next one. So again, we're going to start with end behavior. So what's the end behavior for example number 2? What does that indicate about our leading coefficient? So maybe write a note for yourself. You can write down to remind yourself we're going to have to include that negative at the end. You can write a little note so you don't forget it. Alright, what are my zeros? Zeros and roots mean the same thing. Anytime I ask for a 0, I'm asking for the x-intercept root as a solution. So it's one of my solutions of the graph. Right here. 1. That's positive 2. So you find your solutions, your x-intercept. And then based off of those, that's how we're going to how we are going to find the factors. We're going backwards. So we know what the x-intercepts are first, and we go backwards to find the factors. So if I know one solution is -3, the factor would be +3. And one factor is -1. One solution is -1, then the factor would be +1, and then the last one would be x -2. There are different signs going back. Alright, now before we write the polynomial, we have to think for a second about our crossing and our bouncing. So what happens at our -3? Crossing, at our -1, bouncing, and then at our 2, crossing. So we're going to have one factor that's bouncing. How do we represent that it's bouncing? A square. So which one of these factors would I square? Whichever factor gives you that point, that's the one that you square. So in our polynomial, f of x equals, we have the negative, because the behavior is negative. Then we have x plus 3, x plus 1 squared represents bounce, and then x minus 2. So I pull all that information together. Alright, so once again, f of 1, you're going to go to 1 on the x-axis, and tell me what the y value would be on the graph. Over to 1, and then you go up to where the graph is. 1, 2, 3, 4. Okay. That's your y value. Okay. You guys might also put a question like this. I want to make sure you're able to recognize this question and know what to do. If I ask you which 0 has a multiplicity of 2, remember multiplicity is just a fancy word for exponent of its factor. So if I ask you which 0 has a multiplicity of 2, I'm asking which 0 has a factor that being which has a factor that squares. That's what it's asking. Multiplicity is a fancy word for exponent. If it says the exponent is 2, that means it's squared. So it's asking which one of these solutions has a factor that's squared. A -1. Okay. So this factor that was squared means that the solution, or the 0, is the -1. So if you see a question like that asking about multiplicity, you need to look for the square. If it's asking for a multiplicity of 2, look for the square, and then write down the x-intercept where that happens. Does that make sense? Alright, let's try the last one. This one's a little bit crazy. Alright, first things first, what is the end behavior? Down, up. So what does the leading coefficient need to be? Well, that needs to be positive. So that just means I'm not going to add anything when I write the final product. Alright, we have a bunch of different solutions, so let's look them out. What is one of my solutions on the graph? -4 on the far left. -1.5. 0. 2. And +4. So we have a bunch. Okay? Now we're going to take each one of those and turn them into factors, because again, we're going to be writing the equation factor form. So what factor would I get from -4? Okay. What do you think I would get from the -1.5? Good guess. So I'm actually going to draw an arrow because that's not what we're going to write, but I'm going to tell you guys how we can change that. So our guess was that we were going to write x plus 1.5, right? It's the opposite of the -1.5. But in factors, you should never ever write decimals or fractions. Ever. Okay, so I'm going to show you the system you can use to change this so it will look like a linear factor that doesn't have decimals or fractions. So the first thing you want to do is convert the decimal into a fraction so we can see what we're working with here. So what would 1.5 be as a fraction? As a mixed number fraction. Now, once you've done this, the only thing you need to do to fix this so it's no longer a fraction is you're just going to swing the denominator over in front of the x, like this. Whatever the denominator would be, swing it over in front of the x. Now, does everybody agree? If I were to set this equal to 0, would I still end up with negative 1.5 after I solve? Yeah. So this is the way that you would want to write the factor if you guys have some sort of decimal or fraction method. So we're going to write it as 2x plus 3 for that factor. Okay? What about for the 0? Let's do this in x, and then for the 2, minus 2, and then for the 4, x minus 4. Okay. Now we need to take into consideration any crossing or bouncing. So if you look at the picture, what do you notice about all the x-intercepts? So do I have any squares? No, you only have squares when they're bouncing. So we're just going to write our polynomial by stringing all of these together. I'm going to write the x to friend, going without the parentheses, friend works out better. And then I'm going to write all the factors. And that would be your polynomial in factor form. Okay, and then again, just going back to remind you guys, because our end behavior was positive, I didn't need to add anything to the front. We're just going to assume it's positive 1 or negative 1 if you need to do that, but since it was positive. Alright, so is everybody clear on how to do the reverse direction of what we were doing last time? Okay. Last thing, if I say that I want to find f of negative 5, so the x value is negative 5, what value would the graph have at negative 5 for x? If we go to negative 5 and then down to the graph, it's right on the edge of the picture, but there's the graph negative 3 that we have in the picture. Alright, questions?